Hello, everybody. Welcome to Physics 4140. That is the upper division, electricity and magnetism. So I want to let you know that you are automatically muted and your video is off when you join the meeting. Now it is totally up to you whether you want to show your camera or not. And if you have a question, of course, feel free to unmute yourself and raise your hand at any time. And I'm really sad we meet in this way for such a wonderful class. It's one of my favorite class to teach. And we have a really big enrollment this year, almost 60 students. Now, I do believe we will do a better job if we could see each other in person. But unfortunately, this is the circumstance we live in. That being said, I understand you all have your difficulties and challenges. Being alone and being at home. Some of you may experience difficulty with internet connection or interruptions if you have family members you need to take care of. I understand and I completely can empathize with that. So if you have any difficulty that you need me to accommodate, I'll try my best to make accommodations. Okay, so also you may notice I have get rid of the participation credits for the online class. So you'll have the freedom to watch the video if you cannot attend our class at the same time. All right. Okay, just one sec. All right. So first of all, I would like to go through the Blackboard site. So to show you where everything is and show you what assignments are due when. And then we will start our discussion about the grading, and then we will do a lot of math today as a beginning of our class. Some of you have already started reading the books, and I'm very glad that happened. All right, good morning, good morning. Thank you for also putting in the chat. First of all, let me go ahead and share my screen so you can we can walk you through the Blackboard site. And this is the browser, okay. Can you see my screen? Just tell me that if you shout out that you can, or if you have, okay. All right.
Yeah,
okay,
we can see it.
so we'll see the screen right now. This is our, I believe we have, have this new format the university put in for Blackboard. So if you're here, start here, and it's telling you a little welcome message. And if I have announcements, I'll send out a lot of announcements. So you should automatically receive an email every time an announcement is set. So I recommend that keep up with the announcement because sometimes if we have important updates on our schedule or some kind of solution that I posted, I will remind you with the announcements. Course information, let's click and take a look at that. There is your syllabus, and this is your tentative schedule of what is due which week and what content we were going to cover. Now, this is only tentative, so if there is a change in due date, that you should go to the weekly assignments. That will be most up to date. But this tentative schedule gives you a rough idea of what is due which week. Of course, if you want to go to the class Zoom link, it's here again. You don't have to go dig it out from the announcements. So I want to let you know that this I sent out a survey on what would be the best time to host office hours. You probably have already seen it. A lot of you have responded as well, but if you haven't, please kindly respond and put in your input by the end of this week, okay? So by next week, we should have finalized our office hours. So I'll try to choose the time that works the best for everyone, for most people. But if you can make it, don't worry about it. You can always just email me and we can set up standalone meetings one-on-one if you need help. Okay, so this is syllabus and tentative schedule. And if you want to see the survey, it's right here. Okay, so next thing I want to show is after each class, you should go to lecture notes and videos. to view the lectures, lecture notes and the video I post each week. So right now, just week 1. Now, if you click it, there is only a activity we will be using on Wednesday. So I post the stuff here. But after every day's class, I will try to update this to include our lecture notes and videos as soon as possible. So weekly assignments, this will be your best friend to keep update with what is due each week. So for example, we are now at our first week. We don't have homework. We don't have a pre-flight. Now pre-flight is done online. I'll talk a little bit more about that later. But there will be an assessment due on Friday, at the end of Friday. This assessment is not counted into your grade. The purpose of such an assessment is for the instructor to better understand what students know and don't know. So it's very informative. So there is no pressure and there's no, it's not a high stake test at all. It's not a test, it's more of a survey to gather some response. So whenever you have time, please click this link and do your pre-assessment survey. And you will be given 1% extra credit for doing this with honest participation, which means you don't randomly click. If you randomly click, we will not gather any useful information. There will be a post-assessment at the end of the semester, and I will post that when the time comes. So right now I'm under the instructor's view. You're not going to see the week 2. I'm seeing the week 2, but it is hidden from you right now because the time hasn't updated yet. By Friday, you will see a week 2 folder. Will tell you what is due. For example, if I click week 2, it will tell you pre-flight is due on Monday and homework is due on Friday. And you're probably very familiar with this already. For submitting your homeworks, you can simply just write it out and scan it, upload it. There is a software that will allow you to take pictures with your phone and generate a PDF out of that. I will post instructions on that later when we get to the homework part. So this is really basically all I need to tell you about the Blackboard side. It's just a few important links. Exams will be given online, and I'll give you more instructions as we get to it. Okay, so let's get back to our grading. So let me connect you through my iPad. So I'm gonna share my screen, 1 second. Okay, so can you all see my new screen right now? Okay.
Yeah, we can.
All right, so anytime if you have some difficulty, just raise your hand and let me know, okay? If I can't hear you or if I don't see your type, just shout out and stop me. Okay, so this is the required textbooks, as you all know, and I hope you, if you haven't already, get a copy of the textbook as soon as you can. I don't really care what edition you can get a second-handed, it doesn't matter. With us being more independent, we're doing this online. Reading the textbook has become more important than ever. So I cannot emphasize enough how important it is to read textbooks. A lot of times the question you might want to ask, if you read the text, you realize, oh, there's the answer. So get the textbook. You are all enrolled in the co-requisite for recitation. That is on Friday. Again, I encourage synchronous participation, but again, it's not required. The participation is not counted into your grade. But it's very important, and that is the key to success in the class, to come to these recitations and practice solving the problems and working it out within the groups and also with me, with the instructor together. So try to come as much as you can. The recitation Zoom will be a different link just because the recording setting is a little bit different. I don't want to use the same link for my lecture and recitation, but you go to the recitation Blackboard site, it tells you which link to go to. Now, again, if you, these 2 sessions, you feel free to attend either of one. I don't really care, but I will be there for the whole time, okay? Okay, so this is basically our grading. The pre-flight is a few questions that I'll ask at the beginning of certain classes. Not usually we'll have 1 pre-flight each week, not all of weeks, but most of the weeks, just to give you motivation for reading the textbook and come to the class prepared. The pre-flights are not graded again. You simply need to put in your honest answer and you get the credit. You simply access the link through our weekly folders on Blackboard. Then the next biggest part that is, I would say, get as much credit as you can for these easier grades. That's the homework, 20%. And again, homework will be uploaded and graded each week online. I will view your PDF and I'll put in your grade in the Blackboard, okay? So the other 3 components are the 2 midterms and final. We always have 2 midterms and 1 final for this class. I'll talk a little bit more about how we want to do the exams as we come to it. So that's it. That's all we have for logistics, for accessing the Blackboard, for the grading. Before I move on to talk about electrodynamics and the math, are there any questions? I see a question for, would it be possible to create a Physics 4140 class in the Physics Discord? And if so, could I post the link in the chat? Of course, absolutely. Thank you so much for suggesting this. And I will send this information in Blackboard to everybody so that we will have a place we can all communicate and have a community, feeling a little bit more of a community. Thank you for that. Any other questions for me before I move on?
Did you have a good winter break, Dr. Rand?
Yes, as good as it can be. Yes, how about yourself?
It was good. Pretty much in the same boat.
Yeah, yes, it's, we all feel very isolated and, but I hear fall class might be online. Really hope to, our life to get back to normal. Any questions? Okay, if you think of anything, just let me know. Shoot me an email or whenever. Okay, so we're beginning this class, electrodynamics. And I said it's probably one of my favorite class to teach. I want to tell you why and hopefully become one of your favorite subject. Look at the grand scheme of physics. If I may draw a little diagram here to share with you, how do we view all the things we study physics? And we always say physics is the study of everything, right? So we study things from small scale to big scale. We study things from very low speed to very high speed. So this is how, this is low speed, this is high speed. Now, we have studied, I'm sure everybody here, the physics branch that study big stuff and low speed objects. And what subject is that? In this quadrant?
Classical mechanics.
Classical mechanics, very good. Okay, so we have we're very familiar with this. And then what about high speed? Again, big objects. In a quadrant.
Astrophysics.
I'm sorry?
Astrophysics.
Yes, yes. And when it's very, in terms specifically, the subject, the discipline that, that
relativity. Relativity.
Yes,
Relativistic.
yes. So we need to switch to special relativity if you're dealing with very high speed. What about something that's really small?
Quantum.
Quantum mechanics, yes. And I believe some of you have already done that and some of you have yet to take the class. Small object, but high speed. Now,
particle physics?
Yes, you need to combine relativity with quantum. So it needs to be relativistic quantum mechanics, and we give it another name called a quantum field theory. Now you can see we have filled our quadrants already. You might wonder, I haven't leave any space for classical mechanics. I haven't leave any space for electrodynamics. Where would electrodynamics fit in this quadrant? Where would it go?
Would it be everywhere?
Could it be everywhere? It is, in a sense that it's consistent with everything else, make it could be everywhere. Unlike Newtonian mechanics, it is not consistent with special relativity. Electrodynamics is consistent with relativity. But however, it is still a classical theory. So we will still put it in here. It is a classical theory. It is classical mechanics and classical electrodynamics. The difference for, but what makes it really special from Newtonian mechanics is that now Newtonian mechanics is, will have big errors when you go to very, very high speed. However, electrodynamics is the same format, whether you're dealing with low speed or high speed. So it is one of the most successful physics theory we currently have. So if I want to, and because of the Maxwell equations and our development with E&M, that actually forced Einstein to think about the implications. What does it mean of the classical mechanics, that the postulates that we sometimes didn't talk about, but we do make these assumptions when we do Newtonian mechanics. So for example, we all assume that all the clocks we measure time at different reference frame are the same time, whether you're timing something sitting still on Earth, or whether you're timing something while you're on the space rocket. In the Newtonian mechanics, our assumption is it is the same time. It's the absolute time. That's one of the postulates. The other assumption is the velocity can go on forever. There's no limits in how high of a speed that we can go. The third is, now that you have the ruler, whether you're moving with the rocket and measure something, or whether you're sitting relatively still with the Earth, you measure the same length, independent of the velocity. Now, these would work if your velocity is low speed, but if you go to high speed, these postulates need to be revised. So when Maxwell formulated his equations, the 4 Maxwell equations, I'm sure you have seen it, and we will spend a lot of time to review it and talk about it here again. By combining these equations together, first he discovered that the propagation of E&M waves is really the same as propagation of light, because the constants coming out of these equations is the speed of light. And we also see this speed of light is invariant in every frame. You don't really have a frame dependence for the speed of light. So because of these, Einstein was forced to consider the implications for the Galilean, the classical transformations, and their obvious underlying assumptions, and inspired him to have the new postulates for special relativity. So instead of time and length being absolute, now it is the speed of light is being absolute, and everything else become relative. So that makes Maxwell equations, and that's one of the reasons that make electrodynamics a very successful theory and have a special place in history. So these are the 4 Maxwell equations. If doesn't look familiar to you, that's okay, because we will spend a lot of time to do this again. So here we have Gauss's law. This is talking about there's no magnetic monopoles. And we have Faraday's law and Ampere's law here. And this is the differential format for the Maxwell equations. So recall in physics 2530, or if you had taken 234 in the quarter system, combining 2 of the equations together, for example, if I combine these 2 together, I will be able to get a wave equation for the E field. Likewise, if I combine them differently, I will get a wave equation for the magnetic field. That is showing us that the E&M waves is really a propagation of this, the light is really a form of E&M wave radiation. And these constants can give us the speed of light. That is something we have done in 2530. And this is something I've talked about already. Here we are treating our measure of length as absolute, time as absolute, but Now, if you want it to be coherent, correct with special relativity, you need to think about time dilation and length contraction. And we will call these Lorentz transformation instead of Galilean transformation. Another reason that why electrodynamics has a special place in physics and why it is so successful is by studying the Maxwell equation, we view that the equation for the E is very similar to the equation for B. So in the sense, the E and B, you can view it as the two sides of the same coin. In a way, you can say we unified electricity and magnetism as one coherent thing instead of viewing it as two separate phenomenon. As we first study electricity and magnetism, we always view them as separate phenomena. Now we know that they can be unified. So following that logic, people and generations of people after that tried to do the same thing to achieve this grand unification. So we talked about 4 different interactions of nature. Add a page here so I could write our notes. So we have 4 types of interactions in nature. Of course, the electromagnetic interaction. Any other interactions?
Gravity.
Yes, gravitational interaction. I'm gonna put that below because that's something we haven't been able to unify yet. We have anything else?
Strong force.
Strong interaction or weak weak interaction, very good. The strong interactions is for what's holding the nuclei together. Now the weak is responsible for the decay process. Now we know about gravitational and electromagnetic already. So following this logic, people had successfully have the electroweak theory to combine these two together. And further on, people think, okay, can we combine more together? We have combined electroweak and the strong together to become the standard model theory. We have yet to combine gravity with everything else, but people are trying hard to do this following the same logic. There's the string theory, and the other theory is trying to combine everything together to achieve the grand unification. So you can see that what people are doing, what Maxwell had set in place for other people to follow is this idea of unifying different phenomena into one coherent theory. That's another reason why it has a special place in physics, why this is a really, really interesting subject. So hopefully I'm giving enough motivation for us to begin looking at this subject for this semester. But first of all, we do need to lay some groundwork for our math. Okay, so today we'll spend some time with our math and we'll spend 2 more classes just on doing the math. Okay, did I add a page? Okay. All right, so I will start by reviewing vectors. I will do that very quickly because later on we will work with the divergence and curls and the Laplacian, the del symbol. So that is a lot of operation with vectors. So first of all, let's review our vectors. And it is very important, but you are already familiar with this part, so I'm going to be relatively fast. So we're working with the dot product of 2 vectors, and you know that A dot into B is giving you a scalar, right? And this called a dot product or a scalar product. So you get AX, BX plus AY, Y plus AZ and BZ. Now you can also do a curl with these. Now, depending on how you want to memorize the final result, for me, I would simply just list them up in the matrices, and a curl into B give you another vector. So you need these components, and you have the component for A, and you have the component for B. Now, to reduce them, this is how I do it. Of course, you don't have to. First of all, you work with the x hat, right? You're left with a 2x2 matrix. You have AY BZ minus AZ BY. Now you're working with the Y hat, and that pick up a negative sign, and you're left with another 2x2 that reduced into this. The third one is Z hat, and you're left with this another 2x2. So this is just a way for me to work it out, and you can do it in your own way, or if you want to look it up, but it might be faster if you already remember how to do it. There are some really quick triple product rules. Again, these I don't think you need to remember because we always can go back to our textbook and to look it up. But something that can be useful later on is we take a dot product between A vector and the cross product of B and C, and that is equal to B dot into C curl A, and is equal to C dot into A cross B. Okay. There's something else I will, again, the curl of A cross into B cross C, and that is equal to B C cross A minus C, I'm sorry, this is a dot. So this is just scalar and this is still vector. C times A dot into B. This is our sum triple product that is in your book. You don't have to memorize this. Okay, so now have quickly reviewed the vectors, we can now work with the divergence and curl, because there's something, a lot of stuff that's very interesting about the vector fields that we can see by looking at the divergence and curl. So let me add another page so we can work on it. So here, let me introduce the delta, the del operator, which is a vector and is going to be operated upon other quantities. So the operator itself is a vector, which means it has x hat, y hat, and z hat. And what operation is going to do is going to take a derivative, right? So y hat is going to take a derivative with respect to y, and is going to take a derivative with respect to z. So this is the delta, this is the operator. And it can be used on a scalar function, it can be used on vector function. So first let's look at, what if we act this operator on a scalar function? So we're going to do a scalar t, and this is a scalar. We are going to put the delta in front of this t. So what do you think this is? We're taking the what of t? What do you guys think?
Gradient.
The gradient.
Divergence. Oh.
The gradient, excellent. This is the gradient of a scalar function. The gradient of t. You can see that simply you just add the t, right? It's operated on t and it's keeping the hat. So the gradient of a scalar give you a scalar, right? Oh, scalar or vector?
A vector.
Give you a vector. It's carried from the del operator. Okay, now we can act on it on a vector function. There are two different ways to act on a vector function. So let's call it a vector v. If we do del dot into v, a dot product between the operator, the del operator, and a vector, that gave us a scalar. This is called the divergence, as you said earlier. And you can see, how does that work? d dx, d dy, d dz, dot into Vx, Vy, and Vz. It has 3 components, right? Any vectors, you can express it in terms of 3 components. Okay, so if we continue to work this out, we have dvx dx, dvy dy, and dvz dz. Okay. The third, you can act on a vector function, but you take the cross product instead, right? And this is called the curl of V, right? And here, I'm not gonna go through the process. I'm just gonna write out the results. I'm gonna show you how to get the results, but I'm not gonna, okay, so this is a cross product. I'm gonna use the thing that we did before. It's the 3 different directions, right? You have this first vector is ddx as the x component, ddy, ddz, and v has 3 components as well. So you can reduce that and get what you need. Okay, so that is a curl. Now, we will spend some time to talk about how do we understand the meaning of the divergence and the meaning of curl. And I hope to give you multiple methods to think about divergence and curl. First of all, we will talk about how do you do it simply mathematically, just calculate it. That's, if you know the expression, you calculate it, it would be most straightforward. I also want to give you the perspective, how do you view it using sort of a graphically and using a physical interpretation. That will help us understand the divergence and curl a little bit better. So the word divergence, we'll start with divergence of something, of a vector field, right? So I'm gonna draw, sorry. I'm just gonna draw this point charge.
It's all good.
Okay, sorry. This is a point charge. And we will say that there is a divergence here, okay? And in your textbook, Griffiths talked about, you can think of divergence as sort of something spreading out or coming in the sense that you will have a source of spreading out, or if you have a sink of coming in. So if you can spread some sawdust on water on the piece of, on the lake, and if it starts spreading out, we call there is a divergence. Now the word divergence is a good choice and at the same time is a poor choice, and I'll talk about why it's a poor choice later on. But first, why is it's good to choose the word divergence? Because if you look at something spreading out, it looks as if they are divergent, right? Something are coming in from the center and spreading away, corresponding to having a physical source. As you have divergence, or something draining coming in, then you have sort of a drain, like your bathtub, water goes away. And I'll talk about and put a note on why divergence is a good name, but I will talk about why it's also misleading, can be misleading sometimes. If you'll excuse me 1 second, I need to charge my laptop. 1 second, sorry. Okay, sorry, I'm back. So first of all, I want to show you how we view divergence mathematically. First of all, I'm going to draw a vector field, and you can look at it with me to see if this one has a divergence or not. So I'm going to draw a vector field pointing up. You can see it's quite uniform. It does not change anywhere. And I'm going to call this a y direction and an x direction in here. So we have a field in the y hat direction. Okay. Would you say this vector field, would you say it has divergence or a zero divergence or non-zero divergence?
Non-zero divergence.
So why is that?
It's not.
Zero divergence.
When in doubt, mathematical interpretation is actually straightforward. Let's go to our math, right? So the divergence of something is the x component of that vector taking the derivative with respect to x, and the y with respect to y, and the z with respect to z. Okay, so this vector is in the y hat direction only. So Vx equals 0 or non-zero?
0.
0. It does not have any other component. It has y component only. Okay, so this one is 0, this one is 0, and Vy is the only one that is not 0. Now we needed to take the derivative with respect to y. So, okay, so Vy is non-zero and Vy is constant. When I take derivative with respect to y, do I get a 0 or non-zero?
Yeah, you get something.
You get 0.
Like also 0, okay? So this is a vector field with no divergence, with 0 divergence. And you can see it makes sense physically because it's not really spreading away, right? It doesn't seem like there's a source coming in or there's a sink. So mathematically, you can simply just go back to your equations to look at it. I'm going to draw another field. Here, I'm still going to draw the y direction. But you can see as I go up or down, the vector as I go up, the vector becomes bigger. As I go down, the vector becomes smaller. So this field, do you think it has a 0 divergence now or non-zero divergence?
Non-zero.
Would it be a non-zero divergence? Let's see. Is Vy dy. The y component has to depend on the y direction, which means as you change in your position up and down y direction, it is changing the magnitude. Yes, you're right. It actually now has a non-zero divergence. So this field has a non-zero divergence. Okay, so these are mathematical ways we can help us understand divergence. So now let's look at a question. Which of the following two fields, as I show here, has a 0 divergence? So I will give you guys some time to look at this, and I will break you down into groups. So let me see if I could assign you to different groups. I'm just gonna have to do the breakout room randomly. Take about 2 minutes and I'll bring everybody back for a poll, okay? So 55 participants, let's do 14 rooms. You have 3 to 4 people in each room. So I'm gonna go ahead and give you 2 minutes in your breakout rooms, okay? So once you get the prompt, go ahead and accept and join your breakout room and to discuss with your peers. Okay, as we come back, please put in your vote for the question that's being posted. And I have way more choices than we need just to accommodate sometimes we have more choices. But here, just choose from A, B, C, D, and E.
Dr. Ryan, do we put our answers in the chat? I see. Never mind. Okay, thank you.
Okay. All right, we can see that we haven't have all our votes. Majority of votes have already come in. We are kind of tied between B and D. Okay, B is only one is 0, divergence. D said none of them is 0. So why don't we take a look at this together? Okay, so I'm going to end our poll now, okay? Can you all see the results? I'm not sure.
No, we cannot.
Oh, okay, let me just share the results real quick so you can see it. Are you seeing the results right now?
Yeah.
Okay, so we are tied between B and D. Let's get back and look at this together. So this is our screen. Let's look at these two different fields and see whether one of them is 0 and the other is not. Okay, I'm gonna add a page so we can work on it. So let's look at 1. Okay, so I'm gonna call the horizontal is the X direction and the vertical is Y. Let's just call it that. So 1, would you say that vector is in what direction? It's pointing to the left in the X direction, right? So you would say this vector has only X component because only X direction. So this is non-zero. All the other components are 0. So when we do the divergence of this vector 1, we need, this is our math. We're following the math, right? So this is 0, right? Because the components are 0. This is not 0. Does it have a X dependence? What do you think? As you change its location horizontally, does it change magnitude?
Yes.
As you change from left to right, does it change magnitude?
No.
No,
No.
it doesn't, right? So it does not have an X dependence. It has a Y dependence, but that is not what gives us divergence here. So it does not have X dependence, therefore it is 0. So the first vector actually has a 0 divergence. Okay, so this one is 0 divergence. We do the same thing for 2. 2, I think you all agree, right? It has a non-zero divergence because the X direction actually changes direction as you go from left to right. From dvx dx is actually non-zero right now. So the first vector 1 has a 0 divergence. The second vector 2 has a non-zero divergence. So the correct answer is B. Only 1 is 0. Is this one. All right, so this is a mathematical interpretation. I want to give you another way to look at divergence without going through the math. We can call it a conceptual interpretation, or you can want to call it physically. That's 2. So other than mathematically, can we view it differently? So looking at it conceptually, one way is to view it as a flux. So here I'm going to present something we know from math. We're gonna have to borrow something from math and use it for ourselves. It's called the divergence theorem. So this is pure what we know from math. It's telling us now if you are looking at the divergence of some vector over and integrated over some volume that is equal to the surface integration of this vector over some surface, okay? So this is pure math. The volume is defined by this closed surface. So if I have a closed balloon, have a closed spherical surface, I am enclosing some volume. That is the volume of the balloon, right? So whenever you're giving a closed surface, you have defined a volume. So that is how d tau is defined, depending on the area. So this divergence theorem is telling us, well, if this vector has a non-zero divergence, if del dot f is non-zero, which means when I look at the surface integral, we call it, this is like the flux. The flux should also be non-zero. This gives us a conceptual interpretation, or if you rather a physical interpretation, you can call it as well. So let me go draw sort of a diagram to show you what I mean. If there is flux going through some surface, the same amount of flux comes in and the same amount of flux goes out. You will call it what goes in also equal to what goes out, which means there is no flux, right? Nothing is entering it and nothing is leaving it. There is no flux. If there's no flux, there is no divergence. And we know this from the divergence theorem. This is one way to look at this in a conceptual way, is by looking at the flux. And you can see how this might have helped you answer the question previously. If you draw sort of a little area and view whatever comes in, you can see they're all leaving the surface. Whatever goes in goes out, leaving you no net flux. There is no divergence. So this is really quick. You know this right away. However, if you view this here, you can see whatever comes in the right-hand side is less than what is leaving. There is a net flux leaving the area. So there is a non-zero divergence. So this is one way to look at it, is by looking at the flux. So for example, we looked at one vector, right? The second vector is this. If you look at the flux is non-zero. In fact, would you say the flux is larger than zero or smaller than zero?
Larger.
Maybe smaller than zero because a lot is leaving.
What is leaving is larger than zero. Yes, this flux is a dot product with the surface, right? So if this is leaving the area and the area vector is going out, the vector going out, so the flux will be larger than zero. So if the net flux is leaving the area, you have a positive flux. If you have stuff coming in, you have a negative flux. Okay, so this is to view it conceptually, but again, sometimes we need a physical interpretation just to make sure. That's where the word divergence can be confusing comes in. Here I'm going to show you another question. This one we will not vote, but we will simply talk about it together. Here you can see this is our point charge. Okay, so this is a positive charge in the middle, and you can see this is the sort of the vector field of the point charge. I'm going to ask you the divergence in a specific region. I'm not talking about everywhere, but just in this region we're looking at. Do you think we have a zero divergence, non-zero, or do we not know? I'll let you go ahead and put in your votes. We will not discuss in groups now. Okay, so go ahead and enter your answer for this question. Okay, majority of the votes already come in. Let me go ahead and share the results with you. Okay, I'm going to go ahead and end the poll now, okay? Take a look at the results. We have majority voting for B, which is not 0, and some of you vote for A. Okay, 58% vote for B, 35% vote for A. Let's go back to the question and let's think about it together. So what might make you think it's non-zero divergence?
If you broke the two vectors that we do have in the box down to their x and y components, I think as we go to different sections of the box, they would add up differently.
Yeah, here I will talk about mathematical interpretation later, but you can see this is not straightforward as simply just that one dimension. You can see view it clearly increasing or decreasing. Here you have two vectors, x and y. And how, I told you as a point charge, right? I haven't told you a point charge, then you don't really know how these vectors are going to change exactly with respect to x or y. So kind of try to work it out mathematically would be more challenging. So what might be, so you can see that, yes, if we're thinking about simply just the word divergent, oh, I'm thinking spreading apart, right? I will go ahead and choose B. That is totally reasonable. What might prompt you to think it's a zero divergence though? So for those of you who have chosen 0, what might be your reason?
Since the vectors in the region aren't changing, the flux would be 0.
I see. The vector's not changing. Well, it is the vectors may not be changing, but when you do flux, you are integrating over some kind of area. So the area would not be the same, closer or further, right? So actually, to do this particular integration using the flux idea, because I have told you it's a point charge, you know it's a 1 over r squared thing, right? Is KQ 1 over r squared as in E field, and it's in the r hat direction, right? So to do the flux, we will have to choose sort of a spherical shape. In order for the dot product to go away, we would have to choose to look at our area sort of like that. Okay, so some comes in, some goes out. So sort of like shape like that. So you can see that to do the flux, yes, you seems to have more coming in than you go out because the vector field become weaker and weaker as you go further out. But I'm also integrating over a large area, and the area is increasing by an r squared, 4 pi r squared, and your vector are decreasing by 1 over r squared. So they sort of cancel out, actually giving you a 0 flux. Now you can see the mathematical way of doing this is quite difficult, and thinking about diverging in the diagram is confusing. That might cause you to choose B, but the correct answer is indeed 0. Now that is why we need the physical interpretation help us to put a check on our results. So let's go back to look at our divergence theorem. And by using the divergence theorem, we can start from the integral format of Gauss's law and derive the differential format. So I'm gonna do this with you together. So Gauss's law tell us E dot into dA for the electric field is Q charge enclosed over area epsilon naught, a constant epsilon naught. So using the divergence theorem, the left-hand side, this is the left-hand side, I can rewrite it using the volume integral of divergence of this vector. In this case, this vector is E, the volume. So this is divergence theorem. This is pure math, okay? And the right-hand side is charge enclosed still. And I'm going to here rewrite charge enclosed using the integration of volume density, right? Because the total charge is really the charge density over volume. So it's rho d tau. So the left hand carried over. And you can see that this is true for all kind of volume. So therefore, I can derive then the del dot E must be equal to rho the charge density over epsilon naught. And this is our differential format of Gauss's law. Now Gauss's law telling me that if you have a non-zero charge, point charges give rises to your electric field, right? So it's telling us the source of electric field. And so to have a non-zero divergence, you can see in order for this field to be non-zero, you need to have a source, a non-zero source. So using that idea, you can see that can help us check our results in this question. We will not make a mistake because our source for point charge is only in the middle. You don't have any other sources. So the divergence is really non-zero if I had given you a region that is enclosing the source. If I give you any other region in space, for a point charge, you will say there is zero divergence because the source is only in the middle, right? Is nowhere else. So the correct answer here is 0. So you can see when you're giving a question, think about it mathematically, thinking about it conceptually, looking at the flux, and lastly, think about it physically, will likely to reduce the chance of making mistakes. So there are different tools, toolbox in your drawer. Okay, so now we did divergence. I'm gonna shift gears and let's talk about the curl. The curl is the same. There is a sort of a very intuitive way to look at it, as Griffiths pointed out. It's sort of, if you think of a pond, and sort of the vector is being the flow of the water. Now, if I draw a vector that looks kind of like this, now, one intuitive way to view this is instead of putting a sawdust on the water to see it spreading out, indicating non-zero divergence, you can put a paddle wheel in this field and it's going to spin, it start rotating. So you can think of like the force is pushing the leg in a way that it's causing it to rotate. So that's sort of an intuitive way to think about this, of a non-zero curl. You put a paddle wheel in this, is going to rotate. And that is corresponding to a non-zero curl. Okay. And we can also look at it mathematically. So to remind ourselves, the curl of something is, as we didn't work it out, but I'm now going to write out the results for you. If you to work it out mathematically, it becomes like this: plus y hat dvx dz dvz dx plus z hat so this is our mathematical interpretation. Now let's, you can either think about this intuitively or doing it in the math way. Let's look at another question. So here you can see this vector field. We have looked at the divergence of that before, but now instead we want to look at the curl of this field. What do you think about the curl of this field? I will give you again 2 minutes to talk to people and then we'll come back for vote, okay? All right, as you come back, please put in your vote. Okay, so I'm getting a majority of the votes again. Let me close it and then I'll share the results with you. Okay, the majority of us voted for A, and non-zero everywhere, and then B is the next popular vote, and C. Okay, so would anybody like to tell us that the way they decide whether this is a non-zero curl or a zero curl, or we need a formula to decide? I want to give the majority some confidence that A is correct. Very good job. It is indeed correct answer. So anybody would like to talk about what method did they use to decide?
I could say something.
Okay.
Well, the curl has a component that's a z hat component, and then it's negative dvx dy, and the field is pointing in the x direction and it's changing in the y direction, And that's the only one that would be non-zero, but there is one that would be non-zero. So the
Okay, so you use the mathematical method to get that. Very good. So let's review our formula. It's just 3 components, right? This vector has only 1 component. It has vectors pointing in one direction. That's the x direction. We call it an x component. And you can see everything else is 0. I'm going to cross out the 0 ones. Vz is 0, Vy is 0, Vz 0, Vy 0, and these 2 are non-zero, right? And this one need to be depend on z. This one, it needs to depend on y. It doesn't tell us it depend on z. It's showing a cross section of the vector, but it's filled up in space. But it doesn't say it depend on z. So it does depend on y, right? It as you go up and down, it does change its magnitude. So yes, there is a non-zero results coming from the formula and give us a non-zero divergence everywhere in space. So if you put your paddle wheel anywhere, you can see that it is going to rotate. You can think of the paddle wheel sort of feeling a stronger force on the bottom and a weaker force on the top, and the paddle wheel will actually turn in the counterclockwise direction. I'm sorry, clockwise direction. A stronger force on the bottom, push it to the left. So it's going to turn this direction. So you have a non-zero curl. A is correct. Very good. So so when the vector pointing in some direction, we will have to say it has certain component. But we say this in this case, it has an x component, and the x component has a y dependence. These means 2 different things. It has a y dependence, meaning that the vector itself, as the variable y changes, the vector value changes. And that's different from saying it has a y component. So component, something has a x or y component versus something has x or y dependence is different. So be very careful of the language that we use to say what we want to do. Okay, so again, I want to give us sort of the give us the mathematical groundwork for why the paddle wheel analogy actually works. In order to do that, I need to introduce something called the curl theorem. So we have a divergence theorem, and here in corresponding to that pure math, from our math knowledge, we know there is something called the curl theorem, and it has another name called Stokes theorem. It is telling me to the line integral of some vector is equal to the surface integral of the surface that's defined by the closed line of the curl of this vector. So a closed line here is to have a closed line give us an open surface. So think about it, if you have a closed loop, you have a closed loop, I'll give you a surface, right? Have an open surface. Previously, we have a closed surface give you a volume. So the area is actually defined by the line. This is curl theorem. And why the paddle wheel analogy works, you can think about this as I draw the vector we just looked at. If you put a paddle wheel in here, if something has a non-zero curl, if this vector is non-zero curl, which means sort of the line integration along the vector is non-zero. If you go around, so mathematically, an integral of a line is called a circulation. So you can think of this integration as if you were pushing on the leg of the wheel. Like the line integration is kind of like pushing on it, right? So if you go a circulation, you integrate it along the line. So this is bottom, and you go to the top. You're integrating on the top of the line. You can see the integration F dot into dl on the bottom is not canceling out the F dot into dl on the top, right? Bottom and top. And they're not canceling out, and therefore you will have a non-zero circulation if you integrate it simply all around. If you have a non-zero circulation, meaning it is actually pushing it to turn, and that is corresponding to a non-zero curl on the right-hand side. That's why that is the reason behind our paddle wheel analogy is we're actually looking for a line integral here and tell us about the curl indirectly. Okay. We have one more question. Let's look at this question before we end our class. You're very familiar with these two diagrams already. We have already looked at the divergence. Now I'm going to ask you about the curl of these two fields. I will not let you go discuss, but instead I will open up the poll and let's look at this before we go, okay? So which one of these fields has a zero curl? All right, I'm gonna close the vote. And we are majorly agree on choice C. And would you please tell us, what method do you use to answer the question? Did you use the paddle wheel analogy or did you do it mathematically?
I used the paddle wheel analogy and just noticed if I put it in the middle, the force would be even on any side.
Ah, very good. The paddle wheel analogy is actually reliable. It's not like the spreading out divergence that's confusing. The paddle wheel actually is reliable. Very good. So if you put a paddle wheel here, you can see the leg, the force pushing the bottom leg and the force pushing the top leg is equal magnitude. So it's not going to turn, and that gives us actually a zero divergence. Sorry, a zero curl here. So only 2 is 0. Very good. Excellent. You can do it mathematically with, this is a Vx, which has an x dependence. But in our, you never have this term. This one does not show up in the curl calculation. So, and therefore, the curl of this vector field is still 0. Sorry, was there a question?
Yeah, so I'm just trying to generalize motion. If we were to have a divergence, either our object is moving towards a source or away from a source. If we had a zero divergence, but a non-zero curl, it would be rotating in some fashion. But if both of them were 0, then the object we were observing would be stationary.
And you're saying there is a vector field that has a zero divergence, non-zero curl. Is that what you're saying?
Right, I gave a couple of examples. So I said, if we have a vector field that has a divergence, that means that we have some object or some phenomena that we're observing that's moving away from a point source or moving towards a point source, right?
It's not you need to have an object, but more of you need to have a source that's creating this field.
Okay.
In other words, you can think of as waters, vectors as water flow. There will be a water source, sort of you have a faucet that is constantly pushing water in.
Right. And so if we had a divergence of 0 and a curl of 0, that means whatever we're looking at isn't moving, correct? Or nothing is happening, right?
I think it has a zero acceleration, so it can still be moving.
Whether something, you're thinking putting an object in it, will it be moving?
No, it's not necessarily that. I was just, never mind. It's okay. I'll ask you in your office hours, Dr. Ryan.
It's a very good conceptual question. I think we just need a little bit more time to get to what we wanted to ask. Okay, it's great having you all today on the first day. And if you have any questions, please email me. And as I gather your results for your poll for office hours, I will make announcements on what time I'm gonna meet, okay? All right, don't forget to take your pre-assessment and I'll see you on Wednesday. Just a heads up, we will not have a recitation for the first week. You can simply use the recitation for the time to do your pre-diagnostic survey, just to make sure that you have enough time to do it. Okay, I'll see you on Wednesday.
Thank
Bye,
you, Dr.
everybody.
Ryan.
Thank you, Dr. Ryan.
you.
Have a nice day.
Have
Thank
a
you,
nice
Dr. Ryan.
day, everybody. Bye.
Thank you, Professor.
Bye, thank you.
Professor, I forgot if you put this in your syllabus, but are you going to post the notes that you do in class on Blackboard?
Yeah, I will have my handwritten notes and along with the solution for the slides. It's pretty much everything I've written already. Yeah.
Okay.
On the Blackboard. Yeah.
Okay, thank you.
All right, no problem. All right, I'm gonna go ahead and end our meeting, okay?
Yeah, thank you.
Bye.